Good morning, dear friends. I am Dr. Reginam Linus from Sanjay Godawat University, Kolhapur, Maharashtra. In the last session, we understood that what is meant by diode, what are the construction, working of the diode, then what are the types of diode with the activity. Under this activity, where we have seen what is the characteristics of general purpose diode, fast recovery diode and the Schottky diode, and also we did the interactive book activity as well. In this today's lecture, we are going to learn about what is the relation between reverse recovery time with the total reverse recovery charge and the reverse recovery current and the total reverse recovery charge. Also, what is meant by S factor or softness factor. So all those parameters are the common parameters for the power diode, so that one can select the power diode based on the reverse recovery time, reverse recovery current or peak recovery current, and the total charge, reverse recovery charge. So let us go to the presentation. Outcome of this today's session is one can understand the relation between reverse recovery time and the charge or the reverse recovery charge. Then second one can explain the relation between reverse recovery current and the reverse recovery charge. Also, you can explain the softness factor and the importance in power diode. Dear friends, those who have not subscribed this channel, kindly subscribe. I have recalled this diagram from our previous session. We have seen that there is having a reverse recovery time. What is reverse recovery time? The time interval between the anode current goes to 0 and return back to 25% of the total reverse maximum current. So that is called as reverse recovery time. So the reverse recovery time having the two subdivision, that is T1 and T2. Some of the books you can see TA and TB as well. So what is the time T1? The time T1 is nothing but that is the time required the stored energy in the depletion layer, so stored charge in the depletion layer has to remove. So for that time we required the time required at which the stored energy in the stored charge in the depletion layer has been removed. That is called as T1. Or otherwise one can define it as T1 is nothing but the time interval between the time at which that anode current below goes to 0 and the time at which the anode current reaches the reverse maximum current. Then similarly T2 is nothing but that is the time period in which the charges in the semiconductor layers removed, or otherwise the time interval between anode current reaches the maximum reverse current and the 25% of the anode current reaches the 25% of the maximum reverse current. So that is the screenshot. We already learned it. For this understanding of this session, explanation is very much necessary. That's why I have explained. The friends, those who have not gone through this video, just to go to the session as 7 and understand and come back to this portion. Then another one, if you see here this diagram, if you see here, this is a zero reference, right? Zero reference. You can see it seems to be like one triangle. More or less seems to be like a triangle. Let me draw the triangle. In this triangle, this distance is nothing but TRR. Already we know reverse recovery time is nothing but TRR. Then this current is the reverse maximum current. So we have written here reverse maximum current, the distance. Then we have formed the triangle like this. So this is called as T1 and this is called as T2. TRR is nothing but T1 plus T2. So now if you see here, this is called as the rate of change of current with respect to time, correct? This is the rate of change of current with respect to time. So we can say this as di by dt. So now if we see this only this triangle, only this right angled triangle alone, we can separate like this: IAM, di by dt and T1. So at the steady state condition, di by dt is nothing but maximum current at this point. What is maximum current? Maximum reverse maximum current, right? Reverse maximum current. Di by dt is nothing but maximum current divided by the total time period. So we can write di by dt is nothing but IRM divided by T1. Then from this we can, from this equation 2, we can calculate IRM is nothing, we can derive IRM equal to T1 into di by dt. I hope you understand how the derivation will be. So assume this equation as equation number 1. Assume that this equation is equation number 1. Then second one, already I told you that when I explained the Schottky diode, there is no reverse recovery time for Schottky diode. Why? There is only aluminum metal is there. So the energy stored in the semiconductor will drastically reduce since there is no holes at all. So by considering this, we are taking it as TRR is nothing but T1 alone. What is T1? The time period at which just charges stored in the depletion layer removed. We are not at all considering this. So therefore, so we can write approximately TRR is nothing but T1. So in this first equation you can substitute this. So we will get IRM equal to TRR into di by dt. I hope you understand up to this. Then this triangle is here. What will happen in this portion? This is called as T1, this is called as T2. So in this entire portion is nothing but charges stored in the depletion layer plus the time required to remove all the charges stored in the depletion layer plus charges stored in the semiconductor layers, right? Already we have seen these two waveform figure 1 and figure 2, you can understand. So this, if we want to know the total charge enclosed in this region, how we can calculate? This is like a triangle. So the area of the triangle is nothing but total charge, reverse recovery charge. So for that, what we have to do? What is in by area of the triangle? Half in the breadth in the height. So this is the height and this is the breadth. So height is IRM and breadth is nothing but TRR. TRR nothing but T1 plus T2. So half IRM into TRR. So we can write QRR equal to half IRM into TRR. So from this we can calculate IRM is nothing but 2RR divided by 2 QRR divided by TRR. I hope you understand. Already we have one IRM here, and based on the charges, reverse recovery charge, IRM equal to 2 into QRR divided by TRR. Now what we are going to do? We are going to equate this equation 1 and equation 3. Right? So then from once we equate equation 1 and equation 3, we will get the value of what is meant by TRR. Our ultimate aim is we have to be understand what is meant by reverse recovery time, charge, reverse recovery charge and current, and what will be the relation between the reverse recovery time with respect to charge, right? So for that we are going to equate equation 2 and 3. So we will have TRR into di by dt equal to 2 QRR by TRR. Therefore from this TRR we can write that this TRR and this TRR, so TRR square. So we will get TRR is nothing but 2QR divided by di by dt. So square root. TRR nothing but the square root. Then, but from the equation 2, we know that already we have derived this equation. So equation 2, we know that IRM equal to TRR in the di by dt. So I have taken this here. IRM equal to TRR in the di divided by dt. So from this we can substitute TRR in this equation 2. So TRR, if we substitute here, we will get IRM equal to TRR value in the di by dt. So we have here one di by dt and here one di by dt. So I am going to separate this 2 into QRR. I will write 2 QRR in whole power 1 by 2. So di by dt, it is in the denominator. So if I take it to the denominator, we will have di by dt the whole power minus 1 by 2. Then di by dt. So we will get IRM equal to root of 2 QRR in the di by dt. Then conclusion is, from this equation 4 and equation 5, we will come to know the reverse recovery time and reverse peak reverse current or reverse recovery maximum current, reverse current, both are depends on the QRR. So based on the QRR, if QRR changes, automatically TRR and IRM will change. That is the first conclusion. Then second one, how this stored charge will change. So it will be, so this is one case, it is QRR, and another one is it is depends upon rate of change of current with respect to time, right? So rate of change of here also TRR, it is varying with respect to time. Here TRR is also varying with respect to di by dt, IRM also varying with respect to di by dt, right? Then second conclusion, how the stored charge will, already we know current flowing, it is also, charge is nothing but dq by dt is nothing but current, right? So current is directly proportional to dq by dt, that relation is there. Current is directly proportional to rate of change of charge with respect to time. So similarly, the stored charge is also depends upon the current, forward diode current. So that is the second conclusion. And third conclusion is, hence the reverse recovery time and peak inverse current always depends upon the diode current. So first one, from these two equations we come to know QRR is also TRR is depends upon QRR, IRM also depends on QRR, and both TRR and IRM also depends upon with current, with variation of current with respect to time. Then second one, so the stored charges will be always depends upon the current. Already we know that I is nothing but dq by dt. Therefore, the stored charges based on the current. Then third one, therefore, the reverse recovery time and the peak reverse current or reverse maximum current is also depends upon the diode current. So that is the conclusion. So this is the relation between this recovery time, QRR and IRM. I hope you understand. So let us go to the next one. That point is softness factor. So the softness factor is already the same figure. For understanding I have taken to here as well. I already told you there is TRR is splitted into two. What is that? T1 and T2, right? So T1 is nothing but charges stored, the time required to remove all the charges stored in the depletion layer. T2 is nothing but time required to remove that charges stored in the semiconductor, right? Semiconductor material. So from this, softness factor is nothing but T2 divided by T1, the ratio of T2 divided by T1. Otherwise we can call it as the ratio of that time at which the charges from the time required to remove all the charges in the semiconductor and the time required to remove all the charges in the depletion layer. Then, so that is why softness factor, other name is called as S factor. S is nothing but T2 divided by T1. So the S factor will help you to realize whether the voltage transient occur during the time diode recovers. So when during the diode recovery time, whether any voltage changes, transients are occurring or not, that is depends upon the S factor. S factor will help you to understand what will be the voltage transient occur during the reverse diode recovers. So now, when assume that softness factor or S factor is greater than 1. So if some diodes F factor is greater than 1, S factor. So those diodes have what S factor is greater than 1 means, what it means? T2 is more, right? T2 is more. So it will take relaxed time to recover, control the reverse recovery process. So it will take more time, relaxed time. This time will be extended. T2 is extending. So as the T2 is extending means this diode will take relaxed time or controlled time, and it will take smooth time to complete all the reverse recovery time, reverse recovery process. So that's why it is called, when this S is greater than 1, the diodes have the gradual and controlled reverse recovery process, and but at the same time as their process of changes are very less, the frequency is very less, the movement is very less. So what will happen? Their electromagnetic interference, so exhibit, there is having the they will exhibit electromagnetic interference due to the absence of sharp current changes. So their electromagnetic interference are very less, since it is going it will not be, the changes in the current are not sharp, it is a smooth way, therefore electromagnetic interference is not there. So applications are wherever we need switching, we need to reduce the switching noise, especially power supplies and audio equipment. We require this diode, the diode which is having softness factor greater than 1. We will call this type of diode is called a soft recovery diode. That means softly, smoothly recovering the recovering process is going to happen. There is no sharp changes in the current. So due to that, there is no electromagnetic interference, and there is no it will gradually, it is moving. So it is a smooth to move. So that's why it is called a soft recovery diode. Then another one, when S is less than 1, means what? Less than or equal to 1. Either these two time period are 1, then only S equal to 1, or otherwise T2 is less than T1. So when T2 is less than 1, that means immediately switching happen off to on. So those diodes have fast and unexpected reverse recovery process. So you will not get sufficient time T1 and T2. Certainly T1 and T2 will happen, this time period will be very less, T2 time period will be very less. So therefore S will be less than or equal to 1. So those diodes have fast and unexpected recovery process, reverse recovery process. So they exhibit high switching speed. So so that what will happen, it will generate significant electromagnetic interference. Then third one, these applications are the places where we will give the importance of efficiency. Wherever we require the efficiency, that time unnecessary time to recovering process we will not give, we will concentrate on the efficiency. So where we will use this diode which has the softness factor less than 1, and wherever the people are not bothering about electromagnetic interference, somewhere electromagnetic is not at all a big concern, so the less concern, that places also this type of diode will be used. So this diode is also called it as hard recovery diodes. Hard recovery diode means what? hard, changing is very hard, current is changes are very steep way. So that is called as hard recovery diode. I hope you understood now what is mean by soft recovery diode and what is mean by hard recovery diode, where the soft recovery diode will give the importance and where we will give a importance to hard recovery diode. Hi friends, I hope you understood the concept of reverse recovery time and reverse recovery charge storage, and as well as that reverse recovery current, and what will be the relation between reverse recovery time and the charge stored, as well as reverse recovery current and charge stored. Also you have learned what is mean by softness factor, what is mean by hard switching diode, and what is mean by soft switching diode. Then I hope this topic is understandable and interesting. The friends, those who have not subscribed this channel, kindly subscribe, kindly comment on it and give your valuable suggestions. Also you can provide the likes button if you really understood the concept well. Wish you all the best. Thank you.